All right, class. This is an example of a projection. I'm doing it in the same context that we worked on in class, where we have results of a preference survey. We're seeing how good of a match two different people are. We have Alyssa Wall and Dillingham Munster, and I just picked the first three values under their names. It doesn't, right off the bat, it doesn't look like they're very good. Here you can see play piano, opposite extremes, and fixed cars, they're opposite. And here there's a neutral versus a negative. So it doesn't look like it. So because I saw that, I drew the values we'd end up with a negative value when we do the projection. So the projection is going to drop a perpendicular here, and then this point, we'll keep green. The projection will be this new vector right here. I should have done that in green. So here in blue, that will be the new vector. That'll be the projection. It looks like we'll end up with a -1, so it'll be some vector pointing in the opposite direction of Alyssa's with some length. So I wrote down the formula. Down here, I just substituted Alyssa and Dillingham with A and D for their vector to keep things short. And the formula over here is just the one from the book, or the one we derived in the peanut butter book. The way it's written now, it's because they simplified some things, it's hard to interpret what this means right away. But we do know the dot product divided by the lengths of both. A and D would be the cosine of the angle, but we're close. But some things we simplified out to keep it smaller, but it makes it less interpretable. One thing I will point out is that this denominator, sometimes people will write it as A dot A, but that's just the same as the length of A squared. So the length of A has the square root of the square of all the components, but A dot A is just the square of all the components, so it doesn't have the square root. So these two things are the same. So you'll see it both places. Another thing I'd like to point out is that this is a vector here, but this is just a scalar. So it is just scaling the Alyssa's vector. We're projecting onto Alyssa's. If we're projecting Dillingham onto Alyssa, we're just going to get a scale, some scale of Alyssa's vector. So the dot product is a scalar in the numerator. The dot product in the denominator is a scalar. You just get a scalar divided by a scalar. So let's go ahead and do this, see what we end up with. So I'm going to start by finding the dot products. So a -1, 1, a -2, dot 0, -1, 2, divided by a -1, 1, a -2, dot a -1, 1, a -2. And that's all multiplied by a -1, 1, -2. Notice 4 of the 5 vectors I just wrote down were Alyssa's vectors. And so then we can actually start calculating the dot products. In the numerator, we're going to have a -1 times 0, plus 1 times a -1, plus a -2 times 2. In the denominator, we will have a -1 times a -1, plus 1 times 1, plus a -2 times a -2, and multiply that all by a -1, 1, and a -2. And we can simplify the numerator. We end up with 0 minus 1 minus 4, and here we end up with 1 plus 1 plus 4 times that vector, and that gives us a minus 5/6 times a minus 1, 1, 2, or that's a minus 5/6 times Alyssa's vector. So what does that mean? Well, yeah, they're not a good match. This is almost 1, so it's almost the direct opposite. The projection of Dillingham onto Alyssa ends up going about the same distance in the opposite direction. It's a minus 5/6 times Alyssa's vector. So this isn't Dillingham, must be maybe something more like that. So that when we drop a perpendicular, we end up around there. So not very good. We could go one more. Like we haven't actually written down all the exact components of the vector. We can continue that scalar multiplication right there. We're going to get 5/6, a minus 5/6, and 10/6. So this is just a minus 5/6 times a minus 1, a minus 5/6 times 1, and a minus 5/6 times a minus 2. And that can simplify. Oops. 5/6, minus 5/6, and 5/3. So that would be the projection, Dillingham's projection onto Alyssa's vector. So thanks.